All right, so let's walk through an example of doing an analysis of variance and then also doing that as a regression. So I'm going to load up rtfm.r data, which has some data on grades and how that is related to attending class and reading the textbook. So I pull this up and there are 8 observations for those 3 variables. So for RTFM1, it's set up this way such that grade is high of 90, low of 35. Attendance is coded 0, 1. Reading is coded as 0, 1. So this is a yes or no. If you have data like that, it usually makes sense to set it up so that 1 means yes and 0 means no. So there's also the RTFM2 data, and that is set up so that that could only be a categorical variable. So you're seeing essentially it's showing the same information, it's just this is in 1s and 0s, and this is in yes and no. So if you try to run a regression with this, it wouldn't run correctly, but you can with this data. So let's run through basically how that works. So first of all, let's cross-tab this data here. So here you see that there is 2 cases of not attending and not reading, 2 cases of not attending but reading, et cetera, et cetera. So this is a balanced model. That's a good sign. So here we're running the aggregate function. And so here you see we have grade as the outcome variable. We have attend and reading. This is coming from RTFM2. And we're getting the mean for all of those groups. So this is basically telling you this is what's going into the ANOVA input, these 4 means. And so when we run the ANOVA, we save it, we print it, and we look at it here. What we see is that there is a significant effect of attendance, and there's also a significant effect of reading at the same time. So what you find is that when you run this effect function here, let's take a look at this. So you're seeing that the means are set up like so. Let's run a regression now with attend and reading. This is using RTFM1 again because it wouldn't run correctly if we didn't, but it's essentially the same data. So if we run this and we get the summary for it, let's take a look at what we're getting here. So we're seeing a significant effect of attendance, and we're seeing a significant effect of reading as well. So it's not a coincidence that the p-value here is 0.00559, and down here it is 0.00559. Same thing here, other one was 0.00079. You're getting different values for this because rather than it giving you the slope, it's giving you the variance associated with it in the ANOVA. And just to show you that it is doing the same thing, let's run an ANOVA on that regression model. So we saved this for running a linear regression. But when you look at this, you're actually seeing that using that exact same data, you're getting the same p-values here. It's rounded to different points, but you don't need to read too much into that. Right. So in that way, if it's a 1 and 0 type of coding, you'll get the same results if you run it as an ANOVA and as a regression, essentially. So how this can be useful is that you can actually change the baseline category, or what's sometimes referred to as the reference group. So the baseline or the reference group is the one that you have coded as 0. So when you're running this, this is usually based on something pragmatic, like what's the easiest to interpret. Like I was talking about before, if you have a yes, and that's a 1, and a no, that's a 0, that kind of intuitively makes sense. But you can run the analysis and you'll get the same results if it's flipped around. It'll just be negative slopes rather than positive slopes, or positive slopes instead of negative slopes. So let's run through an example of that. So let's save regression model 2. In this case, we're predicting the grade based on attendance and based on reading. And so when you get the summary for this, again, this is the information that you're getting out when it's coded this way. So let's pull up RTFM2 from reading and take a look at that. So this is coded as yes, 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 no, 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 yes. Let's split this up so that the reference level is actually yes instead of no, which again would probably be confusing, but in some cases you might want to flip it around. So here we're saving this with the re-level function. And so when we re-level it so that it does yes instead of no, we have X being the data frame, that $sign, and then the variable that we're recoding. And then REF, which will be the reference category, equals whatever you want the reference category to be. This is coded as yes, so we're going to run it as yes. So what we want to do here is I'm actually going to save this as a different variable. So this might be a little confusing, but essentially we're creating RTFM3 from RTFM2 so that we're not overwriting that. Again, if you're creating new variables, you don't want to get rid of the old ones. You want to create a new one and do something else with it. So we have RTFM3 now up here, and now we can do other things with that data frame. So with this, I'm going to actually be saving the re-leveling so that for both of these, yes becomes no, and no is going to become yes the way that the 1s and 0s work. So when we run this, I'll save that regression. It's set up the same way as before, but we're now running it from RTFM3 rather than RTFM2. So it's using the ones that were flipped around, which is 1 and which is 0. And so what you will see here, and let's just take a look at this. For the estimate, -18 instead of +18. For reading, it is -28 instead of +28. The intercept is going to be different. Again, that's going to be kind of hard to interpret. Standard error will be the same. P-value is the same value, but just the opposite. It'll be different from the intercept, but again, you don't have to really worry about that. And the p-values will be the same. So you are getting the same information, but this is a different way to interpret things, depending on what group you want the comparison to be. Another thing that matters for this that we're not going to get into for this class is that if it changes the intercept, this can also change how you would interpret the results. If you start getting into interactions with multiple regressions, which we're not going to get into because it's a bit complicated, how you have the intercept set up will matter, and you can accidentally misinterpret the results if you don't do that. So what I would say is I generally set up the data however you want to interpret it, whatever the reference group is that makes sense. Just make sure that you do that consistently, that you don't flip back and forth, because then if you have one analysis with it set up one way and one analysis with it set up the other way, you might be comparing results from one thing and another thing, and it looks like there's a huge difference, but it's only because the intercept was different for those two. So that's a mistake I have made myself, and now I think about it every time that I run this type of analysis. So the estimates, that is the mean differences, are negative, but they are the same size, and you get the same p-values for that as well. So In this example, it was pretty easy to flip this around because you have the 1 and the 0, just making 1, 0, 0, 1 is an easy way for comparing those two groups. So the contrast coding gets to be a little bit more work if you have more than two groups. So in cases where we have three groups, like with the clinical trial data, that will start mattering. So you can do this using the as numeric function if you have it as category. And with this, we're running with the drug. And when we're looking at drug ANXI-free, basically what we're doing is we're saying if it's ANXI-free, it gives us for 1. If it's not ANXI-free, it's 0. And so you're getting this output here. You're getting 1s and 0s. And so this is nice that ANXI-free is 1. But now all the other data is a 0. So if you just ran this, what you would see is that the other two drug groups, the placebo and the joyzepam, would all be combined together in one group. And we don't want that because that would lead to problems with interpretation. So what do we do here? So what you do is that you have that reference group, and then every other group is considered to be a comparison group. And you basically want to make this 0, 1 variable, which is sometimes called a dummy variable for some reason, for both of those variables. So here, let's use drug ANXI-free, and this is called ANXI-free. We have this saved here, and into this data set, and you could go through each iteration of it. So for example, you could also do this with joyzepam. So like clinical trial joyzepam as numeric joyzepam. If you only have 3 groups and you only have that 1 variable, that's not too bad. You can run those pretty quickly, but it's actually a little bit easier to use the function expand factors. And what this is going to do is it's actually going to create all of those 0, 1 variables automatically for you. So when you have it set up like this, you now see that you're able to get all of those variables included. And now you have the 0, 1 variable for drug ANXI-free, and you have the 0, 1 variable for drug joyzepam. And so generally that's a bit quicker to do. So one thing that is also nice is that the ANOVA and the linear regression, when you have more than 2 groups, is that the ANOVA and linear regression will work the same way if you have those multiple groups as well, in terms of seeing significance between groups. So you can also use the linear model function on the original data if you have it set up a different way. So there's some stuff in the textbook about if you'd prefer to run through the analyses a little bit different way, but that's all going to turn out the same. So that's a matter of personal preference if you want to do it the different way. So another thing that you can do is that you can do different types of contrasts. So what I've shown you so far is basically having one group and then every other group is compared to it. And then when you get each of those tests, what you're getting is whether that reference group and the comparison group are significantly different from each other. You might have other hypotheses about the difference between groups. And so based on your hypothesis about how they're different, you might want to have it set up differently. Because it might be the case that, say, a pair of groups you think are different from each other. So you might want to have the contrast code set up in a different way. So the Helmert contrast is one that's used sometimes. And this is if you want to compare each of the means to the grand mean. So basically, if the mean for that group is significantly different than all of the groups overall. And so for that, you have this contrast Helmert and n equals 5. How this will be set up is just kind of to show you how that works. If you wanted to write out the math yourself and calculate out everything yourself, this is basically how it would work, where one of these is 1 and 0, 2, 3, and 4. So it's basically going up by a number every time that you add in another comparison group to the reference group. So each of these will add up to 0, which these contrasts need to be if you're doing contrast coding. And you will have it work out so that then now each of these comparisons are comparing to the grand mean. So you can also do sum to 0, which also keeps the grand mean at 0, but each group is actually compared to another group. So again, if you were doing this manually, this is basically how it would work here. And so the last group is, or whatever group you want to be listed, is coded as -1, and the other ones are coded as 1. And so this would be comparing the first group to the fifth group's mean, the second group to the fifth group's mean, the third to the fifth, and the fourth to the fifth. And then so essentially you're doing a reference group for each of these. But with this being contrast coding, again, the mean for all of these is going to be 0. So there is a default here that you could do in R. If you always want to have the contrast set up a specific way, you can run through doing this. I'm actually not going to run through all of this manually, but essentially you specify how you want the contrast to be run. And if you don't want the default, if you want the default to be Helmert, what you do is you say options, and options is used for a lot of the defaults in R. You would say contrasts is the thing that I want to change, and you're using the combine function, and you're saying, for these two circumstances, now I want this to be the Helmert contrast. So maybe it's something that you wouldn't use all the time, but if you get used to running more things in R, you can start customizing the defaults for a lot of these functions. I think this one was an example because Helmert contrast is something the author might use a lot. So that's just one example, but this generalizes to a lot of different things. So one thing I would say is that if you're changing things for running a few analyses and you're not going to always do it, when you're changing the options in R, this is one of the only things where if you run it in the console or through the script, it's actually going to keep that on after you close up R. So if you're running a series of analyses and you want them all run the same way, and you don't want each and every test in the future to be run that way, you need to always remember to put it back to the default. And if you do have it different than the default, you might want to let other people who use the same computer know that that's the case. That's part of why I'm not running this myself, because I don't want to forget to get rid of that. Because I'd be very annoyed if I ran my actual analyses for a study and I forgot that the contrast codes were different. All right, so next, let's jump into talking about doing comparisons between specific groups. So you'll remember from the one-way ANOVA that we can do basically t-tests for comparing each pair of groups. You can also run all of those comparisons using the two-key test, referred to as two-key HSD, which will do that for a factorial ANOVA. And this works essentially the same way. So it's not too bad to do all of those comparisons, and then you get the adjusted p-value for this. If you only have a few different comparisons, But let's say you're doing it like in model 3 where you have the interactions. Now what's going to happen is that you'll get every possible combination of those 6 means being compared to each other, and also the marginal means for comparing the larger groups to each other. So this isn't even that complicated of an interaction. It's 2 by 3. You can imagine if you start doing even more interactions that this isn't going to make sense, and you're just going to have a long line of stuff that you accidentally printed out. So another thing too is that the p-value is going to be adjusted by a lot here. You can change it so that it doesn't adjust the p-value, but then you have more type 1 error because you're running so many different individual tests. So if you have a more complex ANOVA, often a lot of times you have specific hypotheses. You think that one specific group or one combination of conditions is going to have the highest means. And you can do those specific comparisons. And essentially what you do is you specify those 2 groups, and you can do t-tests for those in particular. If you specify those ahead of time before you collect the data and before you analyze the data, you don't have to adjust for the p-values, but that does have to be something that you hypothesize ahead of time. And in that case, you would maybe run the t-tests for one group and for another group, or one combination of groups and another combination of groups. And then that would work the same way as those tests for the one-way ANOVA. All right, so the next part got quite complicated, and I realized it was a bit complicated, and then when preparing this lecture, I realized just how detailed it got. I don't think you need to know that much about type 1, type 2, and type 3 sum of squares comparisons. And so what I would say is if you do run into a circumstance where it's an unbalanced design, there aren't exactly the same number of observations per cell, which can happen a lot. I'd say to stick with the standard type 2 sum of squares. If there is circumstances where for some reason you're asked to do type 1 or type 3, you can read into this and learn a little bit more about that. But I do want to run through an example of how to do that, because again, your data is probably going to be imperfect when you run it, so there won't be exactly the same number per cell. I will say before I get into this, if you can control it, try to make those cells as equal as possible in terms of the number of participants, because even though you can account for this a bit, that violation of assumptions, it will become more and more of a problem, produce more and more bias, and you'll have to do more and more of a correction the more unequal they are for each other. So this does not make up for that issue. And by the time I get to the end, you'll understand why that's the case. So I'm actually going to pull up some coffee data here. So it is coffee.rdata. There are 3 variables and there's 18 observations. So here I'm going to get the means. So let's pull this up here quick. So what we have is some coffee information that it's either yes or no for the milk. It's no sugar, fake sugar, or real sugar. So it's basically a 2 by 3 design here. And you get these 6 means that come out here. So this is looking pretty similar to what we did before. However, the problem comes up when you do the crosstabs and you see, okay, how many are in each group? So these are unequal. So if these were all 3, that would be nice. They're not, so there's going to be some bias. So essentially, we're going to want to run the linear model, LM function, and we're creating this variable. Again, we can call this whatever we want to. We're just calling it mod for purposes here. So we have saved that we want a model in which babbling is predicted from how much sugar and milk are in the coffee, or whether there's sugar or not, and whether there's sugar or not, or it's fake, or whether there's milk or not. I messed that up. And that's coming from the coffee data frame. So we have ANOVA, and it's being run on mod. And the type is 2. So this is specifying that it's a type 2 sum of squares. Again, I would just use that all the time. So for the type 2 sum of squares, you see that you are running this and you are getting essentially the same output as you had for the other data. It is going to be adjusting the sum of squares and the F value. So for the eta squared, let's take a look at this, because this is actually the main thing that will be different, and it's potentially a little bit confusing. So the eta squared and partial eta squared are interpreted the same way here. And if we print this out, let's take a look. Oh, wait, I forgot to run this one. So we have created ES, which saves the data from eta squared. Now we can look at it. I'm just not going to edit that error out. It's almost the end of the semester. I'm not going to fix every single error that I make from now on. Anyways, hopefully that's my last error until the end of the semester. But anyways, we have the eta squared, the partial eta squared, and the residual information here. So we have the effect of sugar, we have the effect of milk, sugar and milk, and the residual. So one thing is that if you sum up the eta squares from all of those, you'll remember that eta squared is supposed to add up to 1. So what happens is that this actually does not add up to 1. So if you didn't realize this, you might run this and think, oh, something went wrong. So this is always going to happen when you have an unbalanced model. And so there's that like 3.6% of the variance that is left over even after the residual. So it's kind of the residual of the residual in a way. That is, even when you run the model and you have all the variance left over, because that model is unbalanced, there's basically variance that could not be accounted for at all. And this problem will become more and more of an issue as you have more unbalanced data. So in this case, remember when we were looking up here, this is a bit unbalanced. It's 1 smaller here than if it was 3 in all of them, and it's 1 more here than if it was 3 in all of them. So definitely not ideal. You're basically missing out on like 3.6 of the variance. That's going to affect your power to detect an effect. It's also potentially going to affect any estimates of population parameters a little bit. And then also might result in harder to interpret results. If it was really, really unbalanced, it would be a lot harder to make that work. Like if this was 1 and this was 5, for example, you'd see that there's a bigger percent of the variance that isn't accounted for. If you had a situation where there was no data for some of these cells, then this wouldn't run, because essentially if it did run, it would go down to 0 variance that you can account for, because the interaction isn't able to be calculated when that's the case. And it also does not make sense to calculate the main effects. So it basically tells you main effects can't do it, interaction can't do it, so there's nothing I can do. So that's something that you would want to take into account when you're running things. So this is a bigger problem when you have smaller sample sizes, because it's harder to keep things balanced. So what I'd say is generally just randomly assign your participants to conditions, and it's usually going to be pretty close. You can account for it by using type 2 sum of squares. and you're going to be missing out on a little bit, but it's not the end of the world. If you do have a very small sample, say it's very hard to collect participants, like you're having people go through an MRI, or it's a rare group that you're trying to study, and there's only like 12 people that you can reach. In that case, you have to start being very careful about making sure that you have the same participants in each condition and each combination of conditions across the experiment. So that's all that I have for talking about factorial ANOVAs. You see here, it works very similarly to a typical ANOVA. Sum of square stuff, eta square stuff is very similar in this as well. You could do a lot of comparisons of individual groups. It's basically just adding in an additional level of complexity. So if you did go beyond this, there is tons of different analyses, and essentially all these are going to be building off of that linear model once you get beyond this point for the most part, or it'll be a type of regression beyond the linear model. For this class, you have gotten the basics in what everything else is built on. You definitely don't know how to run all the statistics, and you'll never be able to learn all of them, obviously. But at this point, you should be able to, based on whether your data are categorical or continuous, and how many variables you have, be able to figure out how you would analyze the data, and then how you would interpret the data, and also what problems you might look out for, such as violation of assumptions. So that's it for this chapter. The only thing that I have left is a quick wrap-up video, and I'll jump over to that.